Welcome back, Math 30-2. So today we are going to do, let me go back up here, modeling data using exponential functions. So we are going to do just kind of regressions, really. We're just going to do similar regressions that we've done before. I'm going to show you both ways on the TI calculator and the Desmos. Some of you have asked about the TI calculator. How do I know it's a good regression? Apart from looking at the graph to see if it fits properly, remember that you can also go into the catalog here. So go second catalog. And if your calculator has been reset, this is probably changed. And you want to go down to the Ds. You want to go to diagnostics. So you can just scroll down, but you can also go alpha D as well, I believe. Here's D. Well, let me go down there. What maybe we did? Alpha D. Yeah, there we go. Alpha D. It goes down to the Ds for you. We want to go to diagnostics. So I'm going to turn that on. So diagnostics on and off. I want to make sure that's on. Hit enter. Hit enter again. Oh, you actually want to quit out of this first. When you do it, you want to do it on the regular screen here. So second catalog, alpha D. Alpha D, come on. Stupid thing. Oh, there it is. Okay, we found it. Just took a little bit of time to refresh. Go down to diagnostics on. Hit enter again. It should say done. So that turns on this R square value, which helps us determine, is it a good regression? Now, we're in the exponential, so all we're going to do is just exponential regressions anyway. So what we're going to do from these next sets of graphs here is just determine, are these exponential, these three things here, are they exponential? And this fourth one here, we're going to just use, it says here, use exponential regression to do it. I'm going to answer some questions. These first three, I want to determine, are they exponential growth or decay? Are they neither? Is it good to use those? All right. So if it is exponential, I want to know if it's decay or growth as well. Is it increasing or decreasing? I could just circle the answer here. All right. So there's a few ways to figure this out. You can find out a common ratio, but we can just look at the graph data, because sometimes the data here is not going to be the best to determine that. So I'm going to put this data into my calculator. So here's my calculator. I'm going to go this side over here. Okay. And all that. So there we go. So remember on your calculator, do this on the TI calculator. I'm going to go stat. I'm going to go edit. And in the first column, I'm going to put all the X's. So on the top there, so it's 0, 1, 2, 3, 4, and 5. In the second column, I'm going to hit the other one. So I don't have to put all the 0.000s. I just have to put 2. Because if I put those in there, they're just going to get rid of them for me anyway. 12.5. 31.125. 31.25, sorry. 78.125. And 195.32. Oh. Yeah, there you go. 125. Okay. Got all the data in there. I think it's all correct. Everything lines up nicely. So I'm going to go zoom. Well, first I'm going to go y is equal to, get rid of the stuff that's in here. Go up to the plot first. So I'm going to turn on the plot 1. Okay, once the plot 1 is turned on, now I can go zoom stat. So stat, I believe, is number 9, I think it is. Yeah, there it is, zoom stat. So there's my data. Looks like I messed one of my data points up. This 0, 1, 2, 3 data point. This is too low. So I'm going to just double check that. Oh yeah, I messed that up. It should be 31.25. 31.25. Sweet. Okay, so now I have this data in there. Go graph there. I'll put the data points. Now this definitely looks like an exponential growth to it. All right. So what I'm going to do is I'm going to go stat calc and just double check the R square value and see what it's like. So I'm going to go down here to EXP regression. Okay, so EXP regression. Hit enter on that. I can store this. Remember, you can store this in here. So you can go to vars, yvars function there. So you just go over to yvars, hit function number 1, and then pick an equation to put it into. Now, if you have one of the neurons, you can also go alpha trace, and it lists all the y values out for you. Go down to calculate, You notice my r squared is 1. You want your r squared to be 1, or as close as 1 as possible, like 0.999 or so. If it's like 0.8 or 0.6 is not a very good regression. Okay? You notice that it tells us two things as well. Our A and our B. Our A is my y-intercept. Remember, that's one of the characteristics we can read from this. And the B is your ratio, what your times in by each time to get to the next number. And it's bigger than 1. So that means this is a growth function. We can see from the graph too, it was going upwards. And the regression here is going to be y is equal to, and you got 2 times 2.5 to the power of x. And that's what that's saying. There's the AB to the power of x. And the A and the B here. Cool. So that one worked out. So I'm going to do for this one here, I'm going to type in the data for this. So I'm going to go stat. I'm going to go back to edit. Now to clear these out really quickly, you can go up to L1 here and hit clear enter. It just clears out that whole row really quickly. Clear enter. You can also go into second mem where it says clear all list, number 4 there. So second plus number 4, and then hit enter. It should say done, and that should clear the list out for you. Let's go back to stat edit. I'm going to punch in these numbers 0, 1, 2, 3, 4, 5. Okay, so those are nice numbers. And 0, 2.1, 4.2, 6.3, 8.4, 10.5. Okay, so that's, I'm not liking this. It looks pretty like you're adding numbers each time, like 2.1, 2.1, 2.1. It looks like you're adding 2.1 each time. And remember, exponential is you're multiplying by something each time, not adding each time, but you're multiplying by each time. So I don't think this is going to be very good. So I'm going to probably say it's neither. But I'm going to go zoom. I'm going to go stat. So it's a pretty straight line. This other line here is from the previous regression. That doesn't look very exponential. It's got to have that curve too. It's going up or kind of coming downwards as well. It's not very good in terms of that, but I can also go stat, calc. Let's go down to exponential. That's 0 there. I wrapped it around the other side, so when you hit the up arrow at the top, it just goes to the very bottom. So EXP. I'm going to store this equation. So alpha trace, I'm going to put number 1 here. Nope. I'm going to go to, what did I do wrong here? Oh, it just doesn't work. That might be it. If it doesn't work like this, it gives you an error domain. It's probably neither. If it's a really nice linear one, so if I go back to my stat here, quit, sorry, go stat, go over to calc and do the linear one, AX, this one here, the number 4, lin reg AX plus B. I'll probably get a really good equation out of this. Yeah, there it is. Very nice equation, actually. Perfect for a linear equation. So that's neither. I'm just going to get rid of that part. You don't need that part. Okay, so let's double check this last one here. Is it a... It looks like if it's going to be an exponential, it's going to be decay. The numbers are getting smaller. Let's double check. Stat, edit. Oh, I got stuck in here. I'm just going to go clear those out first. So second plus number 4 clears that out. So let's go back to stat, edit. 0, 1, 2, 3, 4, 5. Awesome. And then 7,047, 23,049. 783, 261, 87, and 29. Okay. Zoom stat, so zoom number 9, or just go down there. Zoom number stat. Looks pretty good, right? I zoom out a lot, so this looks pretty ugly, this y-axis here, but it does look like it's decay to me. So if it is going to be, it's going to be decay. That's what it looks like it's going to be. But let's just double check. So I'm going to go to stat, over to calc. I'm going to do the exponential regression, so number 0 here. Enter, enter, enter. Now, I don't need to see the equation to determine what it is. I don't have to. I'm just going to go calculate. The r squared perfectly 1. It gives us this b value of 0.3 repeating. So I'm going to write this out. It says my A value is 7,047, which makes sense. It's my y-intercept, right? So that's my A value. My B value is 1.3 repeating. What's 1.3 repeating? Is that 1/3? Right? I'm going to double check that. It looks like a fraction, 1/3. Yeah, 1/3. Okay, to the power of x. So it looks like I'm timesing it by 1/3 as I go down. You can just double check that. By going 4,047 times 1/3. Yeah, there's my number, and I can times it by 1/3 again. That's the next one. There's my next one. There's my next one. Yeah, so that's perfect. Cool. Now, these ones fit perfectly. Like this is like perfect exponential growth and decay function. The middle one's not. If it doesn't fit perfectly, our regression is going to work, but it's going to try to fit the data as best as possible. So here is 3 sets of data. Now, you could define, like if I wanted to in this situation, I can make 2007 equal to 0. So I can put it like a 0 here and say this is 1, 2, 3, 4. But you can see later on it says here estimated population at 2002. So you just have to find, or 2020, sorry. You just have to find out where does that land in this chart. Is it the 7th term, the 8th term, et cetera, et cetera, et cetera. Right? Yeah. So we could do that by going here and say subtract 2007. So 2020, oops, 2020, so that should be 20 minus 7. So this would be the 13th term if I were to complete this chart here. So that's going to might be useful for later. So maybe that's what I'm going to do rather than dealing with these really big x values. And it's fine if you want to go really big x values. Then you can go back in time and say, oh, back in 1998 and go back to that. But then you just have to watch out for your range. Or you could just shift everything over. Because you're in these calculators, by going zoom stat, it'll just shift it over for you. So I'm actually going to type in the actual numbers. It makes it a little bit easier to find what I'm looking for. So I'm going to go 2007, 2008, 2009, 2010, 2011. This last one I got to clear out. Oh, I just delete. There we go. All right. I'm going to hit enter. There we go. I probably should clear the list first. Clear the list. Okay. So I'm going to put in these numbers. And you mentioned what it mentions over here. It says that these lists are in thousands. So this is like 3,000 thousands, which is 3.5 million. You just add 3 more zeros to the end of these. So that's what the populations are. They're in the millions, technically. So 3.5 million, et cetera. But I'm going to type the numbers as is into there. So 3,012.7, 3,591.8. So the population is increasing, which is good. Well, I don't know if that's good or not. Okay. Add the numbers in there. Looks pretty good. I'm going to go zoom number 9. There's my data. I can't tell if it's exponential or not. It looks like it's kind of decaying just a little bit. Now, let's see if this data is proper. So let's go stat, calc, exponential regression, because that's what they want. I'm going to store this into y1 and hit calculate. There we go. I'm going to graph that. It looks pretty straight in this picture. The reason it looks pretty straight because how it's zoomed a little bit. If I were to zoom this a little bit back to where it was, so if I go back to my window and I say rather than start at 2000 and something, according to this 2006, let's start back at year 0 for some reason. And my y-min, rather than starting at 3000, let's go back here. So this is what my graph would look like here. And there we are way over here. I don't want it like that, so let's go back to 2000. There's my data. Okay, looking pretty good. What we need to find for this, use exponential regression to define a function that models this. Oops, I got to go back here. Yeah, if we put it with the zeros, the numbers would be like 0, 1, 2, 3. It would be different. So I'm going to go stat, calc, 0. So there's my equation. So it is Yeah, this is going to be kind of ugly because we started off at year 0. So it's going to be a, that's what's going to be a to the times b to the x. So we have some really small number. You can see that this is 1.15, and then this is e to the negative 13. E to the negative 13. The e stands for times 10 to the power of negative 13. So it's a really, really small number here. The b value is the most important part. 1.02. Let's go 2 sig, so 2 decimal places there. And then to the power of x. The regression is not too bad. 0.987. Yeah, not too bad at all. Okay, that's my regression. So I could put in this equation, I could put 2020 into the equation as is, right? Or I can go back to my graph and find 2020. But the problem is my window right now doesn't go to 2020. Max only goes to 2011. So if I were to go graph and I went trace, now watch out when you go trace, you don't want to be on the data points. So it's right now P1, L1, L2, you don't want that. So you want to get off that. You want to be on the line that they created for us. So hit the up or down arrow, and then it'll give us this really ugly equation. So now we're on the line. So I can move around the line all I want, and then hit trace. And then if I go 2020, oops, let's go back there and actually hit the right button. 2020, I should be able to type it in the bottom here, but it's going to be beyond the graph, right? Because it's beyond the graph, we can change the window to at least 2020. The graph there. Now, even though I don't see it up there, the window goes far enough over, I should be able to go trace 2020. Poop on this again. Trace. Hit the down arrow. 2020. There we go. 2020, 4,462. Now, what does that mean in the question? Now, 4,462.391 is in the thousands. So that means I'm going to move this decimal place 3 times over to this spot here. So this is 4,462,391 people. It says to the nearest 10,000s. So that would be like, if I were to round that to the nearest 10,000s, that's my estimation there. Just kind of get rid of a bunch of zeros. All right. When will the population reach 4,200,000? Well, if I get rid of a bunch of zeros, because remember everything's in the thousands here, I'm going to get rid of my zeros here. So I'm going to use 4,200 instead as my number. So I want to know when y is equal to 4,200. So I'm going to go y is equal to put 4,200 in my calculator. Now the problem is I'm not going to see that line because that's beyond this graph. So I go to my window and I want to go up to at least 4,000. Right now it's only going up to 3,800. I want to go up a little bit higher. So I want to go up to, you can go right to the number, like 4,200. I'm going to go a little bit higher so I can see the line. There it is right there. There's my crossing point. So I'm going to go second trace, intersect, enter, enter, enter. So my intersection point here is the year 2016 or 2017. Right? Sometime in the year 2016. In the year 2016. We compare that to like actual population of Alberta if you wanted to. This data was created obviously back in 2011. Okay, so let's try another one out here. What we're going to do for this one here, I'm going to use Desmos to do this one for us. And I'm going to, hopefully I've already shared the file with you, the link. So you just go to the link that I gave you and I'll show up the Desmos regression. I'm going to just load up that website, just 1 second. Okay, so here's my Desmos sheet. Okay, I have lots of Desmos sheets here open for some reason. So this is the Desmos sheet I have here. I've already entered the first set of data. So I got my tilde equation here. This little symbol is called a tilde. It allows us to do the regression. If it was an equal sign, it wouldn't work properly. So this tilde allows the calculator to know I want to do a regression in this form. And this is our exponential form. Okay, so I'm going to type my numbers in here. Okay, that one. And then my next one here. Oh, 4.71114. Perfect. Okay. You got some wonky A value there. The reason I've got a wonky A value is because we didn't start at like 0. Like if I put 0, 1, 2, 3, 4, it'd give us a much nicer A value. And we could do that. You just have to realize that 1998 is not 1998. If I did that, it would be 8, right? But then you also realize that this would be 0, 1, 2, 3, 4. This would be 0, 4, 6, 10, 14, 17. So I just like typing the numbers in as is, but I gotta just change my axes here. To see the graph. There's my graph there. Okay, so I'm just gonna zoom in. Remember, you can just hold down Shift until you see the graph. I knew it was growth, right? I just had to make sure I can see some of my axes here. I probably don't want to see that much because I don't want to go back to the 1400s here. So it was pretty good there. Yeah, so that's a pretty good range of numbers there. It goes from the 1600s all the way to the year 2020 or 2020, sorry. I probably want to just go over here and just change this. I want to see my data too, so I'm going to go all the way up to the hundreds. You see my Y values here go to 111. So I want to at least go to those numbers. So somewhere right about there. There's my data. Sweet. You can do this this way. You can also go to the wrench here and just set it up in here. So like I can say, oh, my data, my X goes from 1990 to 2007. So I can actually type that in there, 1990 to 2007, right? So that's my data there. Just zoom out ever so slightly. So that's what it looks like. There's ever so slight curve to it. My R squared is not too bad, 9984, so it's pretty close to 1. Okay, so this is what I'm going to write down here. So this is nice because they actually, rather than use an E value, they just tell you what A is. A is 1.45. I'm going to go 2 decimal places again. When in doubt, 2 decimal places. Times 10 to the negative 16. So something really small here. Times B, which is 0.0102 again. Oh, that's interesting. Same number as before. To the power of x, because that's ABX. Okay? Use your equation to estimate 1998. So I can put 1998 into this equation, or I can use my graph, because they're going to match each other anyway. I want x here to be 1998. So I can go over here and just type that in. X is equal to 1998. This is the same as hitting trace. Trace, then go 1998. Find that intersection point. So my CIP, CPI, whatever my Y value in this case is going to be 92.44. I'm just going to go 44. Okay. How close was the estimate to the actual value of 91.3? It's pretty close, not too bad, right? They don't give us the 1998 number in here, but the actual value according to this thing was 19 or 91.3. It's pretty close. I'm gonna say that. It's a little bit off, pretty close. Okay. I don't know how long this video is so far. Oh, we're at 24 minutes. I probably had to cut this video in half. No, let's do one more. Okay. There's a lot of useless information in this question here about mice and a bunch of other things. The question is all about coyotes. I don't like question C so much because question C doesn't really involve the regression up here. But it says here, plot the scatter plot, state the exponential regression. So they're telling you what kind of regression to do. So you can either do this in Desmos or not. It's up to you. So I'm going to do this in Desmos because I like the look of Desmos. So that's not the Desmos I want. Let's get rid of that. Preview. Where's Desmos? This one here. That's the Desmos I want. Okay. So I'm going to type this data in. I'm going to go down here to delete a bunch of times. Okay, 0, 1, 2, 3, 4, 5. Okay. And 525, 675, 946, 1252, and 1579. Perfect. Okay. Pretty good R squared, 9959. Not a very good graph here. So I'm going to go my wrench. I'm going to change my data. My x's here, they just go from 0 to 4. So I'm going to go from 0 over to 5-ish, I don't know, something like that. And my y values, my lowest y value is 500. So I'm going to go from 500 to my highest value, 1600-ish. You can type in those exact numbers if you want. Here's my graph. Yeah, it looks pretty good. It looks pretty exponential to me. I like how it starts on the y-axis here. Okay. So we plotted that. That looks good. My regression, it's a much nicer regression. So this is going to be y is equal to 534.62, when in doubt, always two decimal places, times b, which is 1.32 to the power of x. Okay, if the rate of coyotes continues to increase as it did from year to 4, what would it be at year 7? So 7 is my x value. So I could put it in this equation. I could just put an x right in the equation, punch it on my calculator, or just go over here and say x is equal to 7. Oops. I'll put a nice little vertical line for us. So the question here is asking, when x is equal to 7, what is y? Okay, so I just move my graph around, find that intersection point. This ends up being 3,600, and they're not using decimals here. Well, I can't really have a half a coyote or so. So I'm going to the nearest whole number. So that's going to round up to 47 coyotes. Cool. Okay, so this question here just says, the biologists determined that 15,000 would be needed for 770 coyotes. Right, so you need a lot of rabbits to feed those coyotes. How many rabbits would you need to sustain the population at year 5? I don't have year 5 in my chart, because I wouldn't use the number from my chart either. I'd always use the number from the regression. So I'll put an x equal to 5 here instead. So here we have 2,107 coyotes. So therefore, so these 3 dots just stands for therefore. I'm going to take, well, I'm going to create a little ratio here. So I need 15,750 rabbits for every 770 coyotes. So I have 2,107 coyotes. How many rabbits do I need? So it's just going to cross multiply, divide. So pull out my calculator here. Calculator, 2107 times 15,750 divided by 770. Okay, so we would need 43,097 rabbits to sustain this population. That's a lot of rabbits. Okay. The area in which coyotes are studied, or which the coyotes were studied, was approximately 13,800 square kilometers. It was also determined that the maximum population density was 15 coyotes for every 100 square kilometers. Okay, so this is another ratio question. They want to know how many coyotes can I fit in that 13,000. So I can have 15 coyotes for every 100 square kilometers. On the other side of the ratio, I'm just going to put 13,800 and then do a little cross multiply, divide here. Okay, so 13,800 times 15 divided by 100. So this would be 2,070 coyotes. There you go. Now, when would that happen? when would you get 2007? So it's got to be somewhere just before year 5. I know it's beyond the question. I'm just going to put that in there. So I'm going to type in y is equal to 2070 here. Okay. And it says here, yeah, around year 5, we'll have that many coyotes. Otherwise, once you get past that, population density would be too high, maybe. Okay. Oh, 30 minutes. I just cut this video in 2, but maybe I've done that already. And I'll see you in the next lesson. Bye.